Welcome to Dr. Jed's calculus videos. Today's lesson is section 3.1 from Rogowski, the definition of a derivative. In order to be good at this, you need to be good at algebra because there's a lot of algebraic manipulation. You also should be able to graph a function. Whether you're using a graphing calculator or doing it by hand, it makes a lot more sense if you can see what it means. You also should be able to find a limit. This one's not as important because we're not going to be doing a lot of hard limits, but you should understand how to do it in the more basic cases. And it's good if you've seen a difference quotient before. It's not as necessary, we're going to be using them a lot, but if you're quick, you can probably pick it up as you go. So let's see, before we go and actually do derivatives, let's take a look at the idea of a derivative. What a derivative really is, it's the slope of a curve at a point. Now, this is not a line, so it doesn't have a slope. But if you think about it, at any spot along here, there is kind of a slope. So we call that the slope of the tangent line. And I'll draw it right here. I'll try to draw a straight line going right kind of past the curve, touching right there. So we'll call this the tangent line. So how do you find the slope of a tangent line? Well, the best way to find the slope of a line is to use 2 points and take the difference, the rise over run. But we only have 1 point right there, so we have to cheat. We find a point not there, not on the line because we don't know the line yet, but we find a point up here, say, on our curve. That we can do. We'll call that x. And I'm going to erase that. I'm going to call this a now because I want to differentiate between the two. I'm going to find the slope between those two. Oops. Now notice this is a different line, but we're concerned right now with just the slope. The slope is also different. It's close to the line we want, but it's not the same. So how could we get better? We can get better if we pick a point closer. So here's another point. It's closer. It's on the curve still. It's closer than the one we picked before. I'll call that one x now. And I'll find the slope there. And notice this line is much closer to the tangent line we want. Can you see what we're going to do next? We're going to find one closer, and then one closer, and closer, and closer. We're going to take a limit of these slopes. The limit of the slopes is going to be the slope of the tangent line. Now, what is each of these slopes? Algebraically, it's rise over run. Rise over run, the change in the y's, so f of x minus f of a, divide by the change in the x's, x minus a. And if we're going to take the limit of this, we get the formula. Over here, I've already written them. Here's the formula for the derivative. Notice the f prime, that means the derivative. And notice I've actually written two formulas. There are two ways you can write this. They're really the same thing. The first one had it just like before. The x is getting closer to a. The second one we say, well, you know what? Instead of talking about an a and an x, let's talk about an a and how far away the x is. So that distance away is h. Then if we add that on, this is our x. And the distance is h. So it's really the same formula. You might think, why have two? Well, sometimes this one is nicer. In practice, though, this one is usually the one we use. So let's try an example. I'm going to start with an example of this one, and then we'll go on to something with this one. So this one first, coming over here. So let's take a look. The derivative of, here's my function, x squared plus 3x plus 1. And I'm choosing my a, maybe I should say, a is 2. So let a become 2 here. Oh, actually, I'm letting x go to 2, right? So, a is my 2. Here's the formula, just from before. Plugging in f of x, you get this down here. Plugging 2 into the function, you now get 11. Just put 2 squared is 4, plus 3 times 2, plus 1, you get 11. And algebraically, then that simplifies to this. Now, how are we going to find this limit? If you look at it, you plug 2 in the top, you get 0. You plug 2 in the bottom, you get 0. 0 over 0 is indeterminate. You can't just do that. But what you can do with limits especially like this is factor. Do some algebraic magic to simplify it. Let's do that. I'm going to write over here. It's still a limit. X goes to 2. But the top is going to factor, and the bottom is just x minus 2. Now, the nice thing is, since 2 makes this 0, we know one of the factors is x minus 2. Do a little checking and so forth. The other one's going to be x plus 5. See, I said you needed some algebra. That's not hard algebra. It gets worse, sorry. But for now, hopefully that makes sense. What do you do next with limits? You can cancel. Why can you cancel? Because x is getting close to 2. It's not 2. Then if you cancel those, we get the limit as x goes to 2 of x plus 5. And now that's continuous, so we can just put 2 in there. If we put the 2 in there, we get 7. So we have that f prime of 2 is 7. And there you have it. That's how you do it. Let's try another. But this one we'll actually do and find a tangent line. Over here I'm trying something harder, just being more ambitious. X cubed is our function. And we're going to let it be at, again I said x here, I mean a is 1. There's the graph, that's what it looks like. So when x is 1, here's the x cubed curve, that's what the line looks like. When we're done, it better look like that, if we did it right. So let's plug it in. F prime, the derivative, is, I'm using the limit as h goes to 0 formula, so it's f of 1 plus h minus f of 1, divide by h. So now plug things in, plug it into the cube. F of 1 is 1 cubed, that's just 1, that's easy, right here. F of 1 plus h is 1 plus h cubed, and writing it that way is easy. But the thing is, when you cube that out, you multiply it by itself 3 times. Okay, I just did this already, so I'd save some time. That's what you get. Now, we cancel. There's an h on the bottom, so this is easier to factor at the end. But it's messier at the beginning. I'll cancel the 1s. I get 3h plus 3h squared plus h cubed all over h. Now, I have to factor. So before I factored in x minus 2 out, now I'm going to factor in h out, because that's the thing on the bottom. If I factor that h out, let me write it over here. So, factoring the h out of this, I get 3 plus 3h plus, being ambitious with my parentheses there, h squared. The h's cancel. I get limit as h goes to 0 of 3 plus 3h plus h squared. If h goes to 0, I can plug 0 in for h. I just get 3. Now, that's not our answer. Our goal is to find the line tangent to it. That's the derivative. And if you recall, the derivative is the slope of the tangent line. So we know our slope, m is 3. Later we're going to use the derivative as a formula. So to find the slope then, you'd plug the value of x in. But this is a number, so there's no problem. Our slope is 3. What do we do next? We need a point. The original starting point. We know x was 1. That was in the problem statement. Now we need a y. The y value, how do you find that? You plug it into here. It's going to be 1 cubed. And 1 cubed is 1. So our point is 1, 1. Our slope is 3. So how do you do that? To find the line, y is 3x plus something. And the something has to be so that this 1 and 1 work. Well, just doing a little bit of number crunching here. 3 times 1, that's 3. So what better go in here? 1 is equal to 3 plus, well, turns out this be negative 2. And there's our line. Let's take a look at this. Look at the slope. Is that slope about 3? It's an estimate. When you do these graphs, if you do them very precisely, you can measure things very well. If you do them sort of fast and loose like I've done, the graph is not going to be showing the slope too well. But it should show that the y-intercept is -2, or thereabouts. And it does. And there's our example. 2 examples of how to find the derivative on polynomials. Other things, we'll worry about them later. Right now, that's all. So, have a great day, and I'll talk to you again tomorrow.